Okay, so we're going to continue with our lesson in 4.1. This is part 2 of the lesson. So the first thing we're going to talk about are derivative notations. And in this class, predominantly, we're going to look at the first and second derivatives of functions. So I would say our three most common notations for a first derivative are f prime of x. Okay, so if our function is f of x, the first derivative we denote with f prime of x. If our function is y is equal to something, then we can denote the derivative of that as y prime. Or if we have like y is equal to some function, we can also write the derivative as dy over dx. So that would read as the derivative of y with respect to x. And the notations that we can use for the second derivative, if our function is f of x, the second derivative would be f double prime of x. If our function is y equal to some function involving x, the second derivative there would be y double prime. And then if our function is y equal to some function of x, we can also write that as the second derivative of y with respect to x, which would be written using this notation right here. So it looks like d squared y over dx squared, okay? Even though it's not really d squared y over dx squared. So again, that's a second derivative of y with respect to x. Okay, so let's do a quick example involving this. So directions here say that if f of x is equal to rad 2x plus 1, we're asked to find f prime of x and state the domains of f and f prime. Okay, so let's do the domain of f first. I'm going to do that over here on the side. And I'm going to write it in interval notation. So if f is a square root function, we can say that the argument, which is 2x plus 1, has to be greater than or equal to 0 for us to get a valid output. And when we solve the equation for x, we can subtract 1 on both sides and then divide by 2. And that's going to make x is greater than or equal to negative 1/2. So we can write that in interval notation as the half closed interval from negative 1/2 to infinity. All right, now I'm going to do the domain of f prime. I'm just going to write it. We have to actually figure out what f prime is first before we can take its domain. So if we want to find f prime, we're going to do like what we did in the first part of the lesson. So we're going to take the limit as h goes to 0 of the difference quotient. So that's f of x plus h. So when I plug x plus h in the place of x, that's going to be 2 times the quantity x plus h plus 1. And then so I don't have to like write this over again in the next step. I'm just going to distribute 2 across those first two terms. So that's going to be 2x plus 2h plus 1. Minus f of x, which is rad 2x plus 1 all over h. So again, if I try using direct substitution here, we get something of the form 0 over 0. So that means I need to use one of my three techniques again, factoring, conjugate, or simplifying. And I think multiplying by the conjugate is the best choice here. Okay, so I'm going to multiply the top and bottom by the conjugate of the numerator, which is rad 2x plus 2h plus 1 plus rad 2x plus 1. Sorry, I'm running out of space here. And then I'm going to multiply the bottom by the same quantity, so I don't change the value of our fraction. Okay, so when I multiply the top and bottom by the conjugate, in the numerator, we get something of the form a minus b times a plus b. So that's going to multiply out to a squared. So rad 2x plus 2h plus 1 squared is just 2x plus 2h plus 1 minus b squared, which is rad 2x plus 1 squared. Rad 2x plus 1 squared becomes 2x plus 1. So we have to make sure we subtract that entire quantity. And then on bottom, we have h times rad 2x plus 2h plus 1 plus rad 2x plus 1. Okay, so whenever we simplify that numerator, this positive 2x and that negative 2x will cancel. The positive 1 and negative 1 will cancel. So that leaves me with the limit as h goes to 0 of 2h over h times rad 2x plus 2h plus 1 plus rad 2x plus 1. So we can cancel this factor of h on top with that factor of h on bottom. And then when I use direct substitution, when I plug 0 in the place of h, that term right there goes to 0. Okay, so this is going to then become 2 over, we have rad 2x plus 1 plus rad 2x plus 1 in our denominator. So that's going to be 2 rad 2x plus 1. And then this factor of 2 on top will cancel with that factor of 2 on bottom. So that makes 1 over rad 2x plus 1. Okay, so that's f prime of x. Now, if we want to find the domain of that function, there are two things we have to worry about as far as domain is concerned. Number one is what's underneath the argument has to be greater than or equal to 0. And secondly, because that's part of like a rational function, our denominator cannot be equal to 0. So if our denominator cannot be equal to 0, I'm going to change that sign from greater than or equal to greater than. So when we solve that that inequality for x, that's going to give me the domain of f prime, which is x is greater than negative 1/2. Okay, so that would be the open interval from negative 1/2 to infinity. Okay, so what does this mean? Well, the one value that's in the domain of our function but is not in the domain of our derivative is the value x is equal to negative 1/2. So what that tells me, and we're going to see this in 1 second, that tells me that my function is continuous at negative 1/2 because that's in the domain of my function, but it's not differentiable at negative 1/2 because to determine differentiability, you look at the domain of your derivative. Okay, so again, that function f of x is continuous on this interval here, that half-closed interval, and then it's differentiable on this interval here. Okay, and we're going to talk about what differentiability or what it means for a function to be differentiable next. Okay, so differentiability. We said that like continuity or a function being continuous was like a condition for a lot of the calculus theorems that we're going to use later on. Differentiability, a function being differentiable, is also a condition for a lot of the calculus theorems that we're going to use later on as well. Okay, so we can say that a function is differentiable at some point x is equal to c if f prime of c exists. Okay, so if that value c is in the domain of the derivative, then the function is differentiable at that point. And we can also say that a function is differentiable on the open interval from a to b if it is differentiable at every point on that interval. Okay, so if we go back to the previous example, we could say that this function was differentiable on this interval here from negative 1/2 to 0 because all of those values are in the domain of f prime. So our function is differentiable at every single point on that interval because the derivative exists at every point on that interval. Okay, now this is important here, this next theorem we're going to look at. It says that if a function is differentiable at some point x is equal to a, then it also implies that f is continuous at x is equal to a. Okay, so again, if a function is differentiable at x is equal to a, then that also implies that the function is continuous at x is equal to a. But as we're going to note down below, if we take the converse of that statement, so converse means you're going to switch the hypothesis and conclusion. A function being continuous at x is equal to a does not imply that the function is differentiable at x is equal to a. Okay, so again, a function being continuous at x is equal to a does not imply that the function is differentiable at that point. And I'm going to use a function to illustrate this. Okay, and the function that I'm going to use to illustrate this is the function f of x is equal to the absolute value of x. Okay, and with this function here, f is continuous at x is equal to 0, but f is not differentiable at x is equal to 0. If you look at the graph of the function, that function is continuous everywhere. The function is defined everywhere, the limit exists everywhere, and the limit is equal to the function value everywhere. But the function is not differentiable at 0, and this is important here, and we're going to talk more about this just down below. But for a function to be differentiable at a point, okay, I'm going to draw this curve here in red, okay? So for a function to be differentiable at some point, the slope on each side of that point has to be the same, okay? So as we approach the point from the left-hand side in yellow, the slope has to be the same as when we approach that point from the right-hand side. So the slope has to be the same as we approach that point on both sides. And when we take a look at the absolute value function at 0, when we approach the slope from the left-hand side, the slope is -1. When we approach the slope from the right-hand side, the slope is +1. At 0, as we approach those slopes from both sides, those two slopes are not the same, okay? Which means the function fails to be differentiable at x is equal to 0. Okay, the slope has to be the same on both sides for the function to be differentiable at a point. Okay, which is going to lead us to the next thing I want to talk about. Okay, what are the 4 circumstances where a function fails to be differentiable? Okay, and there are 4 instances where a function fails to be differentiable. Okay, the first of which occurs at a corner. Okay, so an example of a function that has a corner is the function f of x equal to the absolute value of x, and that function is not differentiable at x is equal to 0. And again, the reason being is what we said before. When we look at the slope on each side of that point at x is equal to 0, the slope on one side is -1, the slope on the other side is +1. Those two slopes are not the same. Okay? The second instance where a function fails to be differentiable is at a cusp. And an example of a function that has a cusp is the function f of x, which is equal to x raised to the 2/3 power. And as we look at the slope as we approach 0 from the left-hand side, that slope is going to go to -infinity. As we approach 0 from the right-hand side, that slope goes to positive infinity, those two slopes are not the same. Okay, so this is not differentiable also at x is equal to 0. Again, because the slopes on both sides at 0 are different. Okay, the third circumstance where a function fails to be differentiable is at a vertical tangent. Okay, and an example of a function that has a vertical tangent is the function f of x, which is equal to the cube root of x. If you look at the slope of your graph at x is equal to 0, the slope of our graph here, if it has a vertical tangent, that slope is infinity. Okay, which means the slope is undefined. Okay, so again, that function is not differentiable at x is equal to 0. And then the fourth circumstance where a function fails to be differentiable is at a discontinuous point. And an example of a function that has a discontinuous point is the function f of x equal to the absolute value of x divided by x. Okay, and that function is discontinuous at x is equal to 0 for two reasons. Number one, the function is not defined at 0, and also the limit does not exist at 0. So this, again, is an example of a function that is not differentiable at x is equal to 0. Okay, so let's move on to this example. So the next example we're going to look at, the directions say given g of x, which is equal to the absolute value of 3x minus 5, we are asked to find the slope of g at x is equal to 4. Okay, if you guys remember way back at the start of this lesson, how I showed you like the two limit definitions that we had to calculate the slope of our graph, and how I said, like, I hardly ever use this first limit definition. Well, this example here that we're going to look at is the only instance for which I'm going to use this first limit definition. I actually think it's the better choice for us in this particular case. Okay, so let's take a look at these examples here. Again, we want to find the slope of that function at x is equal to 4. Okay, so if I want to calculate g prime of 4 in part A, using that first limit definition, that is going to be the limit as x approaches 4 of g of x, which is the absolute value of 3x minus 5, minus g of 4. Okay, so if I plug 4 into my function, that's going to be 3 times 4, which is 12, minus 5 is 7, and the absolute value of 7 is 7, all over x minus 4. Okay, so if I want to evaluate this limit here, I have to figure out how I can rewrite this absolute value function. And if I pick values that are close to 4, when I plug those values into that expression, we're going to get numbers inside the absolute value bars that are going to be positive. And if we're taking the absolute value of something that's positive, that is just going to be the expression inside of the absolute value bars. So the absolute value of 3x minus 5, because when I plug 4 in, that gives me a positive quantity, I can rewrite the absolute value of 3x minus 5 as 3x minus 5. Okay, minus 7 over x minus 4, which is going to make the limit as x approaches 4 of 3x minus 12 over x minus 4. Now, if I try using direct substitution here, we get 12 minus 12, which is 0, over 4 minus 4, which is 0, which means I should be able to factor this. So if I factor a 3 out, That's 3 times the quantity x minus 4 over x minus 4. I can eliminate those factors, and we find that that limit is equal to 3, which means the slope of our graph is equal to 3. Okay, we can do the same thing at x is equal to 1. So if I want to find the slope at x is equal to 1, that is going to be g prime of 1, which is going to be, using that first limit definition, the limit as x approaches 1 of g of x, which is the absolute value of 3x minus 5, minus g of 1. So when I plug 1 into that function, we get 3 minus 5, which is negative 2, and the absolute value of negative 2 is 2. So that's going to be the absolute value of 3x minus 5 minus 2 all over x minus 1. Okay, so again, we have to figure out how we are going to treat this absolute value expression. So if I plug values in that are close to 1, we're going to be taking the absolute value of something that's negative. Okay, and when we take the absolute value of something that's negative, we're going to rewrite the expression inside the absolute value bars by taking the opposite of that quantity. Okay, so this becomes the opposite of 3x minus 5 minus 2 over x minus 1. And this becomes the limit as x approaches 1 of negative 3x plus 5 minus 2 is going to be plus 3 over x minus 1. Again, if I try using direct substitution, we get something of the form 0 over 0. So I'm going to factor negative 3 out of the numerator, which leaves me with x minus 1 over x minus 1. And we get the slope of that graph to be equal to negative 3. Okay, when we do the same thing with 5/3, we have to look at this closely. Okay, if I plug 5/3 into that function g of x, g of 5/3 would wind up giving me the absolute value of 0. Okay, so what I want to do here is, like, depending on what side limit I take at 5/3, that's going to impact how I have to rewrite the absolute value function. Okay, so what I'm going to do is I'm going to take the limit as x approaches 5/3 from the left-hand side, and we're going to compare that to the limit as x approaches 5/3 from the right-hand side. Okay, so with the left-hand limit at 5/3, okay, so again, using that definition of the derivative, we get g of x, which is the absolute value of 3x minus 5, minus g of 5/3, which we said was 0, over x minus 5/3. Okay, now if, just like we've done with the previous examples, we want to figure out how we treat that absolute value expression. So if I take the limit as x approaches 5/3 from the left-hand side, if I consider values of x that are slightly smaller than 5/3, then when I plug that expression or that number into that absolute value expression, we're going to be taking the absolute value of something that's negative. So if the argument of the absolute value function is negative, we're going to rewrite that absolute value as the opposite of that quantity. So this is going to be the opposite of 3x minus 5 over x minus 5/3. Okay? Now, if I try using direct substitution here, I get something of the form 0 over 0. Okay? Which means I need to, like, manipulate this expression. So the best thing for me to do here is to multiply the top and bottom by 3. So when I do that, when we take the limit as x approaches 5/3 from the left-hand side, we get -3 times 3x minus 5. And when I distribute 3 in my denominator, we get 3x minus 5. So those factors cancel, which makes that slope on the left-hand side equal to -3. Let's do the same thing for the right-hand limit. So the limit as x approaches 5/3 from the right is going to be g of x, which is the absolute value of 3x minus 5, minus g of 5/3, which is 0, over x minus 5 over 3. So again, just like we did with our left-hand limit, when I take the limit as x approaches 5/3 from the right-hand side, if I consider values of x that are slightly bigger than 5/3, I'm going to get a number inside the absolute value bars that is positive. And when we take the absolute value of something that's positive, we're just going to leave the expression alone. Okay, so that absolute value expression becomes 3x minus 5 over x minus 5/3. Again, when I try using direct substitution, we get 0 over 0. So here I can multiply the top and bottom by 3. So we get the limit as x approaches 5/3 from the right-hand side of 3 times the quantity 3x minus 5 all over 3x minus 5. And we can cancel those factors. We get the slope on the right-hand side to be +3. Now remember we said earlier that for the slope to exist at a point, for a function to be differentiable at a point, the slope on the left-hand side has to be equal to the slope on the right-hand side. And that is not the case here. Okay? So the slope on each side of x is equal to 5 over 3 is not the same. So the function is not differentiable at x is equal to 5/3. And basically, like if you were to graph like the absolute value of 3x minus 5, the corner for that function would occur at 5/3. The slope to the right of 5/3 is 3. The slope to the left of 5/3 is -3. And the slope at 5/3, like the function is not differentiable at that point because there is a corner at that value. Okay, so graphically, like that confirms what we found using that definition of the derivative. Okay, so let's get into the next set of examples. So the next set of examples, we're going to take a look at how when given the graph of a function y is equal to f of x, how we can use that to sketch the graph of the derivative, y is equal to f prime of x. Okay. The biggest piece of information I can give you guys here is we want to think about like what points look like on the graph of y is equal to f of x, and what points look like on the graph of y is equal to f prime of x. So on the graph of f of x, ordered pairs look like x comma f of x. So we have some input value, and it gives us some output value, f of x. Now, on the graph of y is equal to f prime of x, ordered pairs are going to look like this. So our inputs are still x values, but the outputs are going to be f prime values. Now, if we think about what f prime measures the slope of the tangent line. Okay, so every single point on the graph of the derivative is going to look like x comma the slope of the tangent line at that point. Okay, so the big key when we're looking at the graph of a curve is we want to identify where the horizontal tangents occur. Okay, so we have a horizontal tangent at this point, and we also have a horizontal tangent at that point. And the significance of that, so if we have a horizontal tangent, we know the slope of the tangent line at that point is 0. So the horizontal tangents tell us where the x-intercepts occur on the graph of the derivative. Because again, the y-coordinate of our point is the slope of the tangent line. And if the slope of the tangent line is 0, that means those are the x values that give us a y-coordinate of 0. Okay, so if I want to sketch the graph of the derivative, I'm going to have an x-intercept at this point, and I'm going to have another x-intercept at this point, okay, where the horizontal tangents occur. Okay, I wish I was in class where I could show you this on like the overhead screen, but I'm going to have to do my best kind of like drawing it and trying to explain it, okay? So once we've identified the horizontal tangents, what we want to do is we want to start like tracking the slope of our graph going from left to right. Okay, so if I start way over here to the left of our graph, I'm going to do this in green, let's say. If I start at like this point way over here, the tangent line is going to be some really steep negative slope. Okay, which means the y-coordinates on the graph of our derivative should be some like really big negative number. Okay, and as I continue like working my way to the right, the slopes are still negative, but the slopes start flattening out, like they start getting closer and closer to 0. So that means the y-coordinates on the graph of the derivative are going to be getting closer and closer to 0 as well. They're still negative, but the slopes are getting closer and closer to 0. Okay, when I look at the points in between the two horizontal tangents, okay, I'm going to do this in black. So when we start close to the left horizontal tangent, like that slope, like the tangent line is positive, but it's not very steep, okay? So it's going to be a positive number, but it's not very big. But as I move my way to the right, the tangent lines get steeper and steeper, okay? So that means that the y values are positive. They're getting a little bit bigger until I get to like this point right here. And then from that point, the slopes are still positive, but they start like getting flatter and flatter. They start getting closer and closer to 0. So that means the y-coordinates on the derivative are positive, but they're getting closer and closer to 0. And then when I look to the right of the second horizontal tangent, I'm going to draw those slopes in purple, okay? So when I start close by the horizontal tangent, like the slopes are negative, but they're pretty close to 0. And as I keep moving to the right, like the slopes get more and more negative. Okay, so the y-coordinates start out being close to 0, and as I move to the right, they get more and more negative. Okay, so the graph of your derivative is going to look like what we have over to the right. Okay, I want you guys to use that same approach to do number 2. So for number 2, that's your function, y is equal to f of x. And then I want you to use that to sketch the graph of the derivative. So go ahead and pause the video and work that one out. Okay, so again, we have three horizontal tangents here. There's the first, there's the second, and here's the third. So that graph is the graph of the derivative is going to have three x-intercepts. So the first one is going to occur like here, second one occurs over here, and the third one is going to occur like right in here. And then all we're going to do is like track the slopes like as we move from left to right. So I'm going to do this a little bit faster than what I did in the first example. Okay, so the slopes over here to the left are steep, but they're positive. And as we move to the right, like the slopes get closer and closer to zero. I'm sorry, the slopes are positive. So that graph has to like start above the x-axis. Okay, so it's going to be here, and the slopes move closer and closer to zero. Okay, in between the first two horizontal tangents, the slopes start out close to zero, but get more and more negative until we get to like this point here, and the slopes start getting closer and closer to zero. So the slopes start getting more and more negative until they get closer and closer to zero. In between the second and third horizontal tangents, the slopes start out pretty flat. They get steeper and steeper. They become more and more positive, and then they flatten out and get closer and closer to zero. So the graphs start out close to zero. They get more and more positive, and then the slopes start getting closer and closer to zero again. And then over to the right of that third horizontal tangent, the slopes start out close to zero, but as we move to the right, they get more and more negative. So the slopes start out close to zero, but as we move to the right, they become more and more negative. So graphically, your derivative is going to look like so. All right, so that's how we go about graphing the derivative of curves. Okay, when we look at 3 is a little bit different. Because like when we have a curve, like we're only like estimating what the value of a slope is, like what our slope is at a point. But if we have a graph like we have in number 3, where it's comprised of line segments, like we can compute the exact slope of line segments. And when we look at the graph in number 3, there are 4 segments that make up that graph. So let's compute the slope of each of those segments. So when we look at the slope of the first segment, to get in between those 2 points, we've risen 3 units and run positive 3 units. So 3 divided by 3 makes that slope 1. When we look at the slope of the second segment, we've risen 0 and we've run 2. So that has a slope of 0. When we look at the slope in between the next 2 points, we've risen -3, or we've fallen 3 units and run 1 unit. So that slope there is -3. And then the slope of the last segment, we've risen -1 unit or fallen 1 unit and run 2 units. So that slope there is -1/2. Okay, so as we mentioned, like if we take all of the points in between the x values of 0 and 3, if I'm graphing the derivative there, the slope is 1, so that means the y-coordinates of all those points between -3 and 0 is going to be 1. Now, it's your choice whether you have an open dot or a closed dot at -3, at -3, 1, but you have to have an open dot at the point 0, 1. And the reason we have to have an open dot at the point 0, 1 is if you look at the graph of your function, the graph of your function has a corner at that point. And we know functions are not differentiable at corners, which means that if a function is not differentiable at a point, the derivative cannot exist at that point. Okay, so that value of 0 at x is equal to 0 cannot be in the domain of our derivative. Okay, when we look between the x values of 0 and 2, the slope of all of those points is going to be 0. So we have to have an open dot at 0, 0. We also have to have an open dot at 2, 0. And again, we're going to draw a horizontal segment passing through those 2 points because the y-coordinates of all of those points is the slope of our graph, which is 0. And again, we have to have an open dot at x is equal to 2 because our graph has a corner. Our function is not differentiable at that corner. Okay, between the x values of 2 and 3, the slope of our graph is -3. So between the x values of 2 and 3, the y-coordinates of all of those points have to be -3. Again, I have to have an open dot at x is equal to 3 because my graph has a corner and the derivative is not defined at a corner. And then between the x values of 3 and 5, the slope of our graph is -1/2. So between 3 and 5, the y-coordinates of all of those points are -1/2. Now again, we have to use an open dot at x is equal to 3 because we have a corner on the graph of f at x is equal to 3. And it's your choice whether you use a closed dot or an open dot at 5. Like this is an endpoint here, so if you want to include that in the derivative, that's fine. If you want to exclude it, that's fine. Either way is acceptable for that. Okay, we'll pick up with part 3 in the next video.